Hi, today we will be looking at distances, and we'll use proportionality to understand distances in terms of velocity and time traveled, and we will apply distances to a problem involving ideal gases. So let's say we're moving at 60 miles per hour, and we travel for 2 hours. So if we travel at 60 miles per hour for 2 hours, we travel 120 miles. 60 times 2 is 120. And so this is written as a mathematical relation. Distance traveled equals velocity times time. And we're now going to use this relationship for a problem involving ideal gases. The mean free path is the average distance a molecule travels after it collides with one neighboring molecule before it collides with a second neighboring molecule. And the question asks, find the proportionality relation between the mean free path and n, the number of molecules in a flask, v, the volume of the flask, and r molecule, the radius of the molecule itself. Now, to solve this problem, we should use Pauli's method, and the first step of Pauli's method is understand the problem. And I think the issue we're facing is we don't yet have a clear picture of what the mean free path is. And so we should start off in understanding this by drawing a picture. Here's a molecule. And it's traveling at a velocity v RMS, gas molecule, and we're looking at the time between collisions. And distance traveled in this case, the time between the collisions, times VRMS, is the mean free path, which I'll abbreviate MFP. The mean free path is the distance traveled, and it is going to be proportional to then the VRMS times the time between collisions. And when you look at this relationship, I think one's first reaction is that if you double VRMS, you'll double MFP. But we wouldn't be right. If you double VRMS, you're moving twice as fast. If you're moving twice as fast, the chance you'll run into another molecule is twice as great. And that means that the time between collisions will be half as much. Doubling VRMS shortens the time between collisions. Doubling VRMS halves t between collisions, and 2 times 1/2 is 1. So doubling VRMS has a factor of 1 change on MFP, which is to say VRMS does not affect MFP. Amazing conclusion. MFP is not proportional. It does not change as VRMS changes. So what does it depend on? And I think we'll need to draw an even better picture. We have our molecule here, and it's going to have a length L. It will have a width W, and both the length and the width are related to the radius of the molecule. And there's our molecule. We can think of it as a sphere with a length and a width, and they trace out as they travel, they trace out a cylinder. The molecule traces out a cylinder. Anytime a gas molecule is inside that cylinder, traced out by VRMS times T between collisions, and whose the radius of the cylinder is L or W, anytime another molecule enters this cylinder, it will collide with the cylinder. And so really the question we're asking is, what is the relationship between another gas molecule entering that cylinder that I've just drawn? So MFP, the mean free path. If I double the number of molecules, then the cylinder will have to be half as big for us to just encounter a single molecule. Doubling the number of molecules will make the cylinder smaller because the chance of our running into another molecule is greater. So doubling N, the number of molecules in the flask, I'll draw a picture of that here. Here's our flask. N is the number of molecules in the flask. Oops. And V is the volume of the flask. And here is our little molecule with its cylinder being traced out inside the flask. And doubling the number of molecules in the flask makes the cylinder smaller in volume by a factor of 2, and therefore doubling the number of molecules is inversely proportional to mean free path. Now let's look at the volume of the flask. As the flask gets bigger, the chance that that my molecule will encounter a neighbor will decrease. So if you double the volume of the flask, the cylinder volume will also have to double. And the cylinder volume is connected to them, is directly proportional to mean free path. So if you double the volume of the flask, you double the mean free path. And then we should turn to L. L is the length of the molecule. As the molecule gets longer, the chance it will run into another molecule increases. If I double the length of the molecule, the chance that I'll run another molecule doubles, and that means that the cylinder, which is where it encounters that single molecule, is going to be half as big. So it's times 1 over length. Doubling the length halves the volume of the cylinder. And the same thing for the width. And we then can write that as mean free path is proportional to 1 over N times V, and both L and W are related to the R radius of the molecule, and we get times 1 over the radius of the molecule squared, 1 for L, 1 for V. And that is the answer to a very difficult question.